Okay, although we're 3 minutes early, I think I'll start, so the schedule is still good. So I'm very happy that Andy Davison from Imperial College London will give a invited keynote here. Andy Davison holds the position of Professor of Robot Vision at the Department of Computing, Imperial College in London, and leads the Dyson Robotics Lab at Imperial College. I think he's most well known for his work in SLAM. I think he's even the one who coined the term SLAM with monoslam by taking the SLAM word from robotics and bringing it over to monocular vision. I think his lab has always led at the forefront of SLAM and what he calls spatial AI. And I'm very happy to now over Zoom get his sort of outlook on how SLAM and spatial AI can be useful for autonomous driving in general, and maybe also how mapping can be a part of this. So, Andy, thank you for joining the workshop.
Thank you very much. Can you hear me okay?
Yes.
Perfect. Okay, so let me share my screen. Great. So can I just confirm that's all coming through okay?
Yes, it looks perfect.
Okay, great. So yeah, I'll make a start. So again, thank you very much for inviting me to the workshop. So I have to, yeah, first of all, I'm sorry not to be there in person. And also, yeah, I'm not really someone with experience directly in autonomous driving. But I will talk to you about my work in scene understanding, 3D spatial AI, SLAM, some of the things that Lucas mentioned, and hopefully you can all understand the connections with hopefully things that you're also interested in autonomous driving, because I think in my mind these different areas and applications of robotic-like technologies are all very closely connected. So the particular thing I will focus on in this talk is real-time neural fields for scene understanding, which is some recent work we've been doing, but I will also refer to some other things that we've been doing over the years. So this all really starts from SLAM and visual SLAM, as Lucas mentioned. So in fact, I didn't originally coin the term SLAM. I think that was probably Hugh Durrant-White's team, as far as I know. But I was definitely one of the people responsible for introducing vision as a primary sensor for SLAM, and bringing that kind of terminology over to computer vision and joining all those things up. So having worked on SLAM and vision-based SLAM through my whole career, so going back to my PhD work in the 90s, it's been quite amazing for me to see that technology, which was just a set of ideas and prototypes in the early days, now find its way into products, and those products have been across various areas. So some of them certainly what we would think of as robotics, so things like robot vacuum cleaners. This is the Dyson 360i, a robot vacuum cleaner, one of the first that had a proper visual SLAM system, and I was directly involved on working on this together with Dyson researchers and engineers. Other robot vacuum cleaners, now often have visual SLAM systems. Certainly products like drones, but then also things we would not necessarily think of as robots, like AR and VR headsets, or even SLAM running within smartphones for various applications. And then, of course, autonomous driving is an area where there's all sorts of SLAM-related technology that's proving to be useful or essential, I think, depending on the point of view of the particular company or approach. But if we look at what these systems actually do in terms of visual SLAM, it's mainly sparse mapping, enabling positioning. I guess that's the key kind of killer app, which was always first in our minds when developing visual SLAM. How does a device with a camera know where it is in a space? So that's now pretty mature technology. working very, very efficiently, low cost sensors and processors and so on. And some of these products are now starting to add extra levels to that, and you can even see some hints of that in these visualizations. So in terms of dense mapping and then also semantic level scene understanding. But I would say those are still at a more kind of early prototype stage. And I think it's also quite clear to say that these are all sorts of early products. I mean, they're not yet super mass market products that everyone uses all the time. I think this is just the start of where things are going. So I've recently been using this term spatial AI to describe a bigger view of SLAM. And for me, it's not like SLAM is one thing and then spatial AI is something we build onto it. For me, it's spatial AI describes what I think I've always been interested in when working on SLAM. We could describe it as basically what is this perception and representation capability that a system can needs, which it builds from its own onboard sensors and processing, and enables the right scene understanding to do intelligent things. So that's how I think of both SLAM and spatial AI. It's representation building from onboard sensors and processing. And one way of thinking of how progress in SLAM has happened is through a series of levels, where level 1 is robust localization, where level 2 is dense mapping, building a detailed representation of the scene. Level 3 might be semantic understanding and actually knowing objects and the identities of things that are present in a scene. And maybe you could think of even more levels that go beyond that. So I've been thinking a lot about the general characteristics of these approaches and spatial AI. I've got a couple of discussion papers labeled, they're called Future Mapping. The first one in particular from 2018 is still, I think, a really relevant thing to possibly read. And what are my views about what a spatial AI system should be like? I think it really comes down to this key point that I think we need to build systems that can build a representation of the world. And it's that representation that really enables useful, intelligent action of a autonomous or semi-autonomous device. And when I say representation, this is an old idea, of course, that systems build representations or maps of scenes. Recently, maybe you might hear terms like world model in deep learning, of saying, here's a system that's going to build a world representation, as if that's a new thing, but it's not. All people working in SLAM have always been interested in building world models. I guess it's just the question of what is that world model? How is it parameterized? How much of it is designed versus learned? I think those are all good open questions to think about. But my instinct is that a useful world model should be somehow fairly close to metric 3D geometry, at least locally, because that getting close to metric 3D gives you the most general ability to reason about a scene. And that's not to say I think it should be millimeter perfect everywhere, but it should be somehow close to metric. And then that level of representation is probably good for many different tasks. And then in the different applications of spatial AI, definitely different levels of representation will be useful. Some will require more accuracy than others. Some might require different semantic categories and everything. But the general character of a spatial AI system may be quite general. So the particular thing that I study and think about in this paper is what are the computational patterns of spatial AI systems? So given that we want systems that can build a representation from sensors and turn that into some kind of model of a scene, what computation does that involve? And in particular, how could we make it really robust? How can we make it really efficient? And I think these computational patterns are really important to efficiency. And that's something I'll mention a little bit more later on. But another general point in that paper is I still think we're pretty far off in where we need to get to in this whole area. We've got some very promising early systems, but there's still an awful lot of work to do. And if we think about the really impactful long-term products in this area, like maybe a general robot for the home that could do all sorts of things like tidy a kitchen, or a general purpose, really low power augmented reality device that you could wear all the time and would really do all sorts of smart things for you, or maybe an autonomous vehicle that really works and works efficiently and is cheap and robust and everything. I still think we've got plenty of research to do to get to products like that. So one project I've been involved in the last couple of years that's been trying to focus a little bit more on, what this whole idea of, ambition in spatial AI is, and what sort of representations it might enable. So I was involved in this. It's a discussion paper called "Rearrangement: A Challenge for Embodied AI." So this is thinking about areas, particularly like home robotics. What is a way of specifying the kind of tasks that you might expect a robot in the home to do? And we kind of came up with this concept of rearrangement as a sort of umbrella term for many different tasks that you might want a robot to do. So obviously tidying up a room is an example of rearrangement, where there's a set of objects that start in some configuration and the goal is to get them into another configuration. But it might also cover all sorts of other tasks, like building something, for instance, is another example of rearrangement. So I was interested in this because, in my view, if your goal is to rearrange a scene, that really motivates this kind of representation-driven approach. So I think if you want a robot to tidy a kitchen, it probably needs to build a pretty powerful 3D representation of the objects and the structure of that scene in order to achieve all of that. So some kind of specific work we've been doing in that sort of rearrangement area and showing how representation is useful is this project that I'll show you. So think about a task like this. We've got a robot and it's faced with some unstructured scene containing objects in a pile, for instance. And what it wants to do is take those objects out and tidy them up somehow. So how's it going to do that? Okay, maybe there's various approaches people are considering which are quite, end-to-end learning. So maybe you just try reinforcement learning on a problem like this. I don't think we've seen really compelling results from systems like that yet. So our approach here has been much more explicit. So we have what I think of as a version of a spatial AI system. So I'm just going to start a video here, which makes observations of this scene from an onboard camera. So there's a camera on the wrist of the robot here. So it's going to look at the scene, and then it's got a suction gripper. So that's its tool to be able to manipulate the scene. Let me just find the right part of this video. So here's the setup here. So the robot wants to tidy away this pile of objects and put them away, some of them onto the shelf, some of them into this box that you can see here. But really the spatial AI component of this is that the robot has, from its camera, it's going to build a representation of the scene. So in fact, in this system, we are telling it in advance. It has a model of its own shape, and it has a model also of these shelves in the scene. And also in this system, it has prior knowledge of the 3D shapes of some of the objects it's going to find. So it does actually start with CAD models of some of the objects in the scene. But you'll see that when we run this system, the robot first observes the scene from several points of view. And what you can see on the right center here is its estimated understanding of the world, where it's got estimated positions and poses of all of the objects that it thinks are important that are present in the scene. But what this scene understanding in 3D enables is then really kind of smart and precise manipulation. So in order to tidy up these objects, it needs to do more than just pick them up in an arbitrary fashion and then drop them. It needs to be able to pick them up in very precise ways so that it can actually place them where it needs to. So what you'll see it doing several times here is picking up an object, but then realizing that's not a pose of the object from which it can directly place it. So what it has to do is drop this object in a certain way such that it can then re-grasp it in the correct way such that it can place it in the way that it needs to. And that re-grasping has been previously learned in simulation. So we've done some previous reinforcement learning to learn about that particular aspect of what's the right way to drop an object so that I can re-grasp it in the way that I want to. But for me, the important point is that this scene understanding, the spatial AI, has enabled this kind of digital twin of going from the real world here to the simulated world here, where the simulated world matches up now to everything that we've learned in simulation previously. So now we can directly map between those two real and simulated worlds. So if you're thinking about things like sim to real, this is really closing the loop on real time, sim to real to sim to real to sim to real. The model is the sim, and the model is always being updated, in real time as the system is running. So that's an example of what I'm talking about. Clearly here with the rather, strong assumptions that we have, solid, quite precise prior models of the objects that are involved in the system. So that's not something that we'll always have. So, what can we do in the case where we don't have such strong prior knowledge? So here's another system called Node SLAM, which makes slightly weaker prior assumptions. So in this system, we assume that we have again, a camera looking at a scene, a depth camera looking at a scene, it captures color and depth images. We're able to recognize instances of particular objects in this scene, but we don't necessarily have specific CAD models for all of these objects. What instead we have is a learned shape model of each of the categories of objects. So in this scene, we have 4 types of objects. We have mugs, bowls, bottles, and cans. Each of those classes of object, we've previously taken a lot of off-the-shelf CAD models for that type of object, and we've done some 3D deep learning to learn a shape space. So for instance, for a mug, we had hundreds of CAD models of mugs. So it's actually a 3D volumetric variational autoencoder that we train such that we now have a controllable 3D model of a mug, which has a low dimensional code, the bottleneck of this VAE, which at runtime we can optimize. So now here's a bigger example. So the camera is going to move around this table. It's going to detect instances of these objects, and for each one that it detects, it's going to bring in this shape model, and then it's going to do a joint optimization of various things. So it's going to optimize for the pose of the camera, the 3D position and pose of these objects, and then also the shape code describing the actual shape of these objects. So in SLAM terms, these objects have now become like landmarks in the scene, but now they're sort of super landmarks that also have pose and shape. But you can see that as we continue to explore the table here, we're just gradually building and improving this, quite detailed and precise object level representation of the scene. And you can really see that this is the sort of representation that would enable, arbitrary, action in this scene, like tidying or pushing or trying to find a safe route through these objects, or whatever that might be. Okay, but still, here we're still making fairly strong assumptions that we know the categories of these objects and we've got these prior shape models. So clearly that's also not always going to work. So I think, we continue to be interested in this whole idea of 3D representation and what is the right way to represent 3D scenes and to represent 3D objects. And that's something that's, we've worked on in many different ways over the years. So in SLAM and dense SLAM, how do we represent the 3D shape of scenes? So we've tried probably every different possibility. So an old work like Connect Fusion, we used volumetric sign distance function representation. We've used volumetric grids in various work. We've used meshes, we've used clouds of points, we've used circles. So all of those different 3D representations have different pros and cons. So we were pretty excited when this kind of new way of representing 3D scenes came along. So that this neural fields idea. I apologize if there's some background noise. We've just got a lot of rain here in London right now. Hopefully it won't be too noisy. So you probably heard about things like NERF and this idea of representing general things in 3D using a neural field, where a neural field is a quite general neural network, usually just a multi-layer perceptron, where the concept is that you feed in a coordinate, and output from that network some property of the scene at that coordinate. So if the network is properly trained, then any coordinate that you feed in, it should output that property. And the most obvious properties to represent are things like the density or occupancy of the scene and the color of the scene. So in the original NERF paper, they also represent the directions of light in the scene. And in some of the things I'm going to show you in a second, we also add other things to that representation. But the first system that we built in this area, so my interest is always SLAM, it's real time, it's representations that we could use for robotics and so on. So NERF was something that was taking hours and hours to train. There are actually now faster versions, things like Instant NGP, which is amazing, or of NERF-like systems. But at the time that NERF came out, we really thought, well, how are we going to make this work in real time and make a kind of demoable real time, mono-SLAM style SLAM system out of this. So we took the NERF-like idea and made several modifications to enable a real-time system. So this is our work called IMAP, which was published in ECCV 2021. So here's the setup. We've got a live depth camera being moved around in a room, and our goal is in real time to make a 3D representation of this scene. So we're going to do this by representing the scene using a neural field. So we need to train this neural field, and we're going to train it in real time. So as we're moving this depth camera around, we're capturing continuous RGB and depth images. We're going to use some subset of those views that we capture as keyframes. So in SLAM terms, for me, this is a bit like old SLAM systems, things like PTAM, that represent maps of scenes by sets of keyframes. So the keyframes you can see gradually appearing in the bottom here. These are the views from the keyframes, and then you can see these red shapes on the main view on the right. These are the estimated positions of the keyframes. So I'm just going to pause it for a second because there's a lot going on here. So the first thing that you'll notice is these kind of red, some of the keyframes are red and and then we've got these red points in the keyframes. So this is one of the things that we needed to do to make this fast enough to run in real time. So whereas in NERF you would use all of the images and all of the pixels and all of the images to try and train the neural field, we're doing some sampling to try and make it faster. So at any point in time, we're continuing to train this neural field using some subset of the keyframes and then a subset of the pixels within the keyframes. So those in the end are these red points here. So these are sampled points from which we're going to take the RGB and depth observation from that keyframe and then render from our neural field. So we do differentiable rendering from our current neural field model, and we say, so that's what this is showing in these views on the left. So if our neural field is already completely correctly representing the scene, then these renders should look, just like the views that we have captured from the camera. If they're not quite the same, then we have a loss that basically says we'll update the parameters of the neural field to make these renders look a bit more like, the actual data that we've captured. And we just basically keep doing that. We keep adding keyframes to our representation. So again, as in something like PTAM, the goal is to have a set of keyframes that nicely span the whole space that we're trying to reconstruct. So in this case, a single room. And the sort of there's a kind of continual learning way of looking at this. So we're continually training this neural network. If we were only just ever showing it, the most recent frame that we'd captured, it would always be trying to represent that well, but would tend to kind of forget about the stuff that old keyframes have seen. So we have this kind of pattern of showing it new stuff, but always also reminding it of old stuff. So sampling views from the old keyframes to show the network so that as it learns new stuff, it doesn't forget about the old stuff. So you can think of this as replay in continuous learning terms. So let me just keep playing this a bit more now. So you'll see it continuing to reconstruct the scene. This gray shape here, the big one, is the current live position of the camera. So I should say the camera position is also being estimated directly within this system. So there's no external system doing camera tracking. It's all done within this system. And you'll see that now so this in real time is probably 2 or 3 minutes. We've reconstructed quite a nice 3D representation of this room. Really, where the detail emerges in this scene is all about where the camera has been. So on the left here, it goes over to look quite closely at this table with some objects on it. And that part of the scene is pretty well reconstructed in detail, whereas other parts, not so much. So what's really interesting about this system is that there's very little design in here. And actually, it's a very small neural network, and it's learned to represent this scene without us having to specify anything like, this is the resolution that you should use. So in terms of scene representation, this is a really interesting thing. And it has this reconstruction some quite nice properties. So when I compare it to older systems, maybe like Kinect Fusion, I think it's true that it hasn't reconstructed the scene with the same precision as a more explicit system necessarily, but it's done some other nice things. It's produced this very nice kind of smooth and complete reconstruction. So in particular, it's very good at filling in holes, places where you've got missing data. It's also even quite good at making a reasonable guess at the shape of the back of objects that you haven't observed. So on the floor here, we've got a football, which we only really observed from the left-hand side, but it's actually made a pretty good guess at completing the shape of this object round the back. And there's no sort of explicit priors in this system. It hasn't seen any data other than what's in this room, but just the fact that it's got to generate this room from a neural network means that it tends to like to reconstruct smooth and complete shapes. So it was really actually that property that makes us think this is a somewhat promising representation for SLAM. And what we really then went on to investigate was how could we use these properties of kind of smoothness and coherence? How could we take advantage of those even further? So the next thing that we worked on was, what if we actually add a semantic channel to this system? So in this system, semantic nerf. So this was published at about the same time as IMAP, and this in fact was not a real-time system. This was using a sort of off-the-shelf, nerf approach. But instead of just trying to learn a representation of the shape and color of a scene, we were also trying to learn a representation of the semantics of the scene. So all that you do, it's really a very simple thing. You add an extra output to the neural network to represent semantics. Just try if I've got the right visualization. Yeah, here we go. So you've got this neural network that's generating normally, color and volume density. Pretty much at the end of the network, you just also add on a semantic output, where the semantic output is usually in the form of a sort of one hot output indicating various semantic classes, where the highest of those outputs is the semantics that you think are present. So now clearly when you're training your system, if you have some ground truth information about semantics, you can also apply that to this head and force this semantic output to be correct. But what we really found in this work was, even if you have very, very sparse or very, very noisy semantic labels available, you can successfully supervise this. And the main reason is that, it's the same network generating color, density, and semantics. So the semantics will inherit all of the kind of smoothness and coherence of the color and density. So because these things are representing the shape of objects and so on, that you can then, with only very sparse semantic information, you can get really high quality semantic segmentation. So we showed various kind of examples of exactly how this could work. Maybe the most interesting one to show you here is a kind of denoising thing. So suppose that as you're training this, the semantic labels that you've got are very, very noisy. So this is so noisy you can barely see there's any kind of truth here. But there is, I think something like, I can't remember the percentage, but a small percentage of the pixels here are representing the correct labels, and the rest are just random noise. When you supervise this thing with this, you can actually then if you then project the labels from the full system, you get these really high quality denoised labels. So instead of being noisy, you can also supervise it with very, very sparse labels. So here's an example here where we're supervising it with very, very coarse labels. So suppose you had a low resolution CNN running on frames, giving you some, very low resolution semantic output. You can then train with that. And then when you reproject, you get this very, very detailed semantic segmentation. And again, the reason for that is because the detail is already there in the network, because the network has learned to represent the shape and color of the scene from which it has, for free, dense supervision. And then you just need to add little bits of semantic supervision to then label the whole scene. So what probably makes it more sense is when I show you the work that we came to after that, which was really putting the previous two systems together. So iLabel is now a real-time IMAP style neural field SLAM system that also has semantic outputs. So let me just play this video. So I think this is probably the best part of it. So here we're going to see the same room sequence that we had before. So the camera's moving around this scene. So this is the same network as in IMAP, but now with extra outputs representing semantics. Now the interesting thing here is these outputs don't even have names. They're just colors at the moment. So because there's no prior data involved in this system at all, we can do on the fly open set semantic labeling. So we have these different outputs available, and at the start they don't really mean anything. So when we first start this system, we have this rep 3D shape of the scene which hasn't yet converged to anything useful, and then it's pretty much painted randomly with these semantic labels. So at each point of the 3D scene here, we're outputting the one of these colored labels that just gives us the highest output, and it doesn't really mean anything yet, but even so, interestingly, you'll see that it's quite coherent. So what we're not seeing is just a random set of noise here. We're seeing kind of coherent blobs, and in fact, if we let this system run for a little while, even without any labels, we'll see some of these blobs tending to attach themselves to objects. So just because the neural field tends to represent the scene in fairly coherent ways. But then what we do in this system, in iLabel, is we now start to apply very sparse labels. So in this system, we do that actually by clicking. So you'll start to see that happening now. So in the view on the left, you'll see us starting to make some clicks to apply labels. So these red blobs here are places where a user has clicked on the scene and told it, this is the semantic label. And then they've just typed in a name. So they've said red is equal to floor, green is equal to ball, blue is equal to wall. But you'll see what's happening, that even though we add just these very, very, very sparse labels, when we then reproject the semantic labels for the whole scene, we get emerging this really, really nice semantic segmentation. And then you can also see the advantage of doing this incrementally. So because this is now a real-time system, the user can always be looking at what the current semantic segmentation is, judging whether it's correct or not, and then adding extra labels as needed. So you might add a couple of clicks to the bed, see that it's already fairly well segmented, and then not need to add any more. Or you might see, oh, that bed looks pretty good, but part of that orange label is creeping up onto the wall. So you just go back and you put one more click on the wall to say, no, actually this part is wall. And so the overall outcome of that is again, within real time, within about 5 minutes, with no prior data here, and around 140, I think it's 140 clicks on the scene, we're able to get this really quite complete semantic segmentation of the scene. So we found that very, very compelling. And in the paper, we show various other examples of quite different settings. So this one is quite interesting because we deliberately apply very, very few clicks. There's 3 clicks on the floor, a couple of clicks on the chairs, and it's not a perfect semantic segmentation, but it's surprisingly good, given that the only labels that have been applied here are about 10 clicks in one image. There's no prior data here at all, and in our current deep learning world, where we're often inclined to think that you need big data sets to learn anything, I think this is very kind of interesting to see. So the very latest work that we've done in this direction, which is in fact just about to be published in Coral, is really going back to robotics with this idea. So we've got a system where a robot is going to make some autonomous interactions with a scene to try to automatically do something like this. So in fact, in terms of representation and how this system works, it's exactly like iLabel, the system I showed you before. So in iLabel, a human is making some sparse interactions to label a scene. Now we're going to assume that the robot is going to make those interactions for itself. So we're interested in interactions that tell us some information that couldn't be determined just visually. So here's an example. We've got a scene here with a pile of clothes, and we want to determine what are the types of materials present in these clothes, so like cotton or synthetics, for instance. So on our robot here, we have a little spectrometer sensor. So this is just a little sensor that shines some different wavelengths of light onto the scene, and based on what's reflected, it can make a judgment of whether this is cotton or another type of material. Now, we can't do that densely. This is just a sensor that measures a single point. So we can go down and make a sparse sample. But that's exactly now like iLabel making a touch. So here, the robot will go and make several kind of touches within this scene. So actually, let's go to the correct one. Here, sorry. So here you'll see that it goes down and it makes these sparse kind of interactions with the scene. And in each case, makes an observation of whether this is cotton or wool or synthetic. So here we've defined the different colors to refer to those different materials. But then when we reproject that label for the whole scene, you'll see that we get this nicely segmented representation, even though the labeling has been incredibly sparse. So we've got another example here of using some touch sensing. So here we are trying to estimate which parts of this scene are hard and which parts are soft. So by just poking the scene, we can use a little bit of force feedback from the robot to make a judgment of whether this is a hard or soft thing. So it's touched this kind of cat pillow a couple of times and judged that that is soft. And now it goes and touches a few of the other places. And it's doing this in a very guided way. So because we're able to generate both the current predicted semantic map here, but also the entropy of that, we know which parts of the scene we're quite sure about and which parts we're still uncertain about. So the robot will always be trying to make extra touches in places where it's uncertain. And you'll see that, again, with only a small number of touches, we're able to get this quite nice classification here into hard and soft within that scene. So that paper is just about to be published at Coral. I'll show you one more thing along this line. So this is another paper we've just recently put on arXiv. So although all of the previous three systems I showed you used no prior training at all, so there's no data set involved, there's no offline learning, clearly that represents a sort of extreme position of, what can we do in this what can we do with no prior learning? That's not to say that I think that's the right thing to do. I think it's interesting to investigate, but clearly we will have prior learning feeding into systems like this. But how can we do that and take advantage of it without being too specific? So that's always the thing I'm worried about once we start to learn from data sets, is that you learn things that are quite specific and difficult to transfer to the actual application domain. So I'm particularly excited about really general sort of priors that you can learn that seem to be very widely applicable. So one of those sort of general priors is just take an off-the-shelf CNN that is trained to do some task like image classification. I'm pretty sure that they're kind of early-ish or maybe all of the convolutional features that a network like that learns are pretty general purpose. And this has been shown, by many different types of systems, that whatever task you're trying to do, CNN features learn something about the natural statistics of images, and they're fairly generalizable. So what if we build a neural field system that's trying to, where we assume that every image will be fed through an input CNN, and then what the neural field is trying to represent is not the actual color of the scene, but it's trying to represent the features in that scene. So we call this feature realistic neural fusion, because rather than thinking of photorealistic, so often that's a term you'll hear in reconstruction and mapping, we're trying to reconstruct a photorealistic model of a scene. In this system, we're trying to build a feature realistic model of a scene. So probably that will make more sense when I show this video. So we've got a camera observing the scene here, capturing depth and color. Now we're feeding every input image just through some off-the-shelf classification CNN. Now that is turning this image into many feature channels, actually possibly hundreds of those from different levels of a CNN. We're not showing all of those here. We're just choosing some of those feature maps and drawing them as colors. So the amount of red, the amount of blue, the amount of green in this image is representing some feature output. And we're doing this at fairly low resolution. So it's a fairly cheap off-the-shelf CNN. But now what we're doing is then fusing those features into our neural field. So our neural field is outputting how much of those features it thinks are present. Think of this as an extension of the semantic nerf idea now to hundreds of feature channels. But the point is now that when we reproject those features, we see, rather than these per image sort of noisy, low resolution, wobbly feature maps, the fused feature maps are much more stable, coherent, and also, we've got detailed boundaries and shapes here. So the kind of little demo of what we can do with that is going back to the iLabel kind of idea of trying to label this scene with very sparse interactions. So we're going to apply a few clicks to this scene to apply labels rather than, so it's a very similar thing to iLabel. And on the left here, we're going to see the predicted semantics for the whole scene. But really the difference now is that in iLabel, we were pretty efficient with clicks, but still we pretty much needed to put some click on every object. Whereas this system is now pretty capable of grouping together similar objects. So we've only made 5 clicks on the scene here. There's different sorts of objects, and some of them are quite weird, difficult to segment objects like socks draped weirdly around this scene. We've just made 1 click on one sock, but it's able to quite nicely segment the other socks in the scene, as you can see in the top left here, even though there are different colors, different shapes, draped over different objects. And that's because, the prior learning ability of the CNN has learned features that tend to be common across different socks. And so therefore we can get this quite nice segmentation in real time in an open set manner, meaning we haven't, some of these categories of objects may not have been present even in, as labels explicitly in the data set we learned from. But the features that are attached to them are quite common. Okay, so I did have more slides on a slightly different topic, but I think I've probably used up all my time. And so I'd like to finish there and make sure we've got a minute or two for questions. So just to conclude, yeah, spatial AI research is pretty exciting, and I still think we're going to be doing it for a long time yet. And to mention my affiliations, which are as a professor and leader of the Dyson Robotics Lab at Imperial College. And then I'm also co-founder of SlamCore, which is a London-based startup doing applied spatial AI solutions. So thanks very much.
Okay, thank you, Andy, very much for the talk. I think you can see this, but the room was packed. People were standing. So if there's any questions, we have a microphone going around, and please ask away. Then I'll start with one question. So I think they are all super nice results, but one thing that I've noticed is that many nerf works are usually for static scenes, and the ones for dynamic scenes are, I think, of much lower quality generally. Do you have any
Yeah.
opinion on how to, or if this is even solvable, or where to go there?
Yeah, so I think it's clear that that's an assumption behind most of the stuff that we're doing. I mean, I would say in most of the stuff I've ever done in SLAM, we've assumed that the world is static, and that's often less of a problem than you might think it is, because I think most of the world is static most of the time, unless there's deliberate agents actually doing things, and you should probably have specific models of agents like people or other cars or animals or something like that. Now we've so in something like the robot experimenter work, we had to think about what tasks we could get this robot to do, and we deliberately chose tasks like poking to determine softness, which would not significantly change the scene, because then our static assumption still works. Now, clearly, that's a bit limiting. Surprisingly, we found some level of robustness to small changes in the scene. So suppose you poke an object and it does slightly move, and you don't do anything explicit in your system, you just keep training this neural field. We have found some nice properties. So for instance, the worst possible thing would be when you move a system, the reconstruction completely sort of disappears and it has to reconstruct that object from scratch. So in something like Connect Fusion, that's what would happen. But in this neural field system, we have found to some extent that when you make a small movement of the object and just keep running, the sort of detailed reconstruction of that object does kind of get dragged over, and even like labels that you've applied to it also get dragged over, at least a little bit. And you might think that when the neural field has learned to efficiently represent that scene, maybe there are some neurons that correspond sort of to the pose of this little detailed object, and it's been able to get a good representation of the slightly changed scene just by changing those pose parameters. So we've seen some evidence of that, but I agree that I'm not sure how far that will go. And so in some other work we're currently doing, we are looking at a much more explicit decomposition. So if we have a multi-object scene, maybe represent it by many small neural field models, and that definitely seems like a way that you can make this go further. But then that does also become a much more complicated system and hard to run in real time. Anyway, my main thing would be this is an open question, and still plenty to do.
Thank you for the answer. Are there maybe any questions online? And there's one in the audience.
Yeah, so can you hear me?
Yes.
Yeah, so thank you for the great talk. So I have a question related to the semantic nerve and iLabel. So it seems like semantic nerve shows some really good results in denoising labels. But I think it seems to me that the noise is kind of like Gaussian. So I wonder how it would behave if there are some mislabels. So, and same goes for iLabel. So if there are some mislabels, maybe if the user accidentally labeled some chair as a desk or something like that, then would it just propagate all those erroneous labels and make the system fail? How does it work in general?
Yeah, that's a good question. I guess this comes down to how do you apply the supervision from those labels. And I think in iLabel at the moment we're applying pretty strong supervision every time there's a label. We're assuming that is a correct label. Whereas if you defined your sort of loss function on that supervision to be something more like a robust kernel, to sort of say, well, every label that's applied, there's a 30% chance that it could be wrong. Then what should happen is, if there's one incorrect label, but 5 correct labels that are saying something else, hopefully those correct labels would overpower the incorrect one, in just the same way as we deal with robust functions and mismatched features in normal 3D SLAM systems, for instance. So I think the system as it is at the moment would probably not work very well if you made the wrong clicks by mistake. But I think there would be ways to change it to make it quite robust to that.
Thank you very much. There is one last question from the audience.
So in the presentation, many are for indoor scenarios. But if we consider about the outdoor, maybe for autonomous driving use cases, there's also many static information on the road, like lane markings, geometry, traffic signs. Do you think if we apply nerve for that kind of use cases will be a good idea?
Possibly, and I think we've seen, you know, some people already trying these sort of methods in outdoor scenes. Things like block nerf, I think, was a pretty amazing outdoor nerf type of system. I guess my instinct would be for things like, you know, signs and things where you do have pretty strong prior knowledge of what those things are. Nerf might not be the best thing to do. I would be more inclined to do something quite explicit and actually fit models that you have of objects like that. You know, I would probably say the same for other cars or pedestrians. You know, use models where you have them, and these sort of methods are good for, you know, a nice, efficient, and often semantically coherent representation of the things that you don't have strong prior models for. So I would often advocate a kind of hybrid representation, and I imagine, you know, in so again, I'm used to thinking about indoor scenes, but, you know, use strong models where you know, if you see a can of Coke on a table, you've got a good CAD model for a can of Coke. Just use it. You know, if you see a you know, a certain model of car, use a model of that. But then there will always be other things in your scene that you don't have good models for, and those might be at some different sort of, you know, representation. And later on, you might get sure enough to upgrade them to something more specific.
Okay, thank you very much again, Andy. I think there's even more questions, but the time is running out, so we're switching to the next presentation. Thank you very much for attending the workshop.
Thanks.